us use an analogy to understand electric flux better. Consider water flowing through a rectangular open channel at uniform velocity and draining into a measuring jar. A valve, V1, is introduced to regulate the quantity of water flowing into the channel. The discharge, which is the quantity of water flowing per unit time, is given by the product of the velocity and area of cross-section of the opening of the regulating valve. To regulate the discharge, we increase the open area of the regulating valve, V1, assuming that the velocity of flow of water upstream remains constant. Let us install one more valve, V2, downstream to V1. V2 is pivoted to the bottom of the channel. Valve V2 can swing about a horizontal axis, which is perpendicular to the direction of flow of water. This completes the apparatus. Now for the experiment. Keep the area of the opening in both the valves the same. That is, the bottom line of the closing plate in the two valves should be at the same height. Measure discharge Q1 for 5 minutes by collecting the water in the measuring jar. Keep this measuring jar away from the downstream flow. Now, lower the closing plate of V1 without changing the position of the plate in V2. Measure discharge Q2 again for 5 minutes. Q2 will be less than Q1 as the area of opening in V1 has decreased due to the lowering of the plate. Then, swing V2 until the bottom line of the plate just touches the top surface of the water in the downstream. Remove valve V1. Measure discharge Q3 again for 5 minutes. You will find that Q3 is equal to Q2. Why is Q3 equal to Q2 when the area of opening of the two valves is different? This is because the area of opening of V2 is more than that of V1. V1 is kept perpendicular to the direction of flow of water, whereas V2 is kept at an angle to the direction of flow of water. The projected area of opening of V2 taken on a plane, which is perpendicular to the direction of flow of water, is equal to the area of opening of V1 that is kept perpendicular to the direction of flow of water. What are the conclusions that we can draw from this experiment? Q is equal to V into A, where V is the velocity of water flow and A is the area through which water flows. In this equation, A should be perpendicular to the direction of flow of water. In the event A is not perpendicular to the direction of flow of water, we should take the projected area on a plane perpendicular to the direction of flow of water. Then, the equation will be modified to Q is equal to V into A cos theta, where theta is the angle that the outward normal to the plane makes with the direction of flow of water. Here, V and A are vectors, and as Q represents the quantity of water, it is a scalar. Mathematically, we can write the equation as Q is equal to the dot product of V and A. Electric flux, phi, is analogous to Q of water. Like Q, phi is also a scalar quantity. However, unlike in Q, where there is flow of water nothing flows in electric flux. There are only imaginary electric lines of force that cut across the area. Uniform electric field E is analogous to the velocity of water V. Mathematically, we can write the equation as phi is equal to the dot product of E and A. We can now extend this equation to curved surfaces with electric field of different magnitudes and directions at different parts of a given surface. The SI unit for electric flux is Newton meter square per coulomb. This brings you to the end of this introductory module on electric flux. You will learn more about applications of electric flux in coming modules.